Welcome to the Deep Dive. We are jumping right into a fascinating topic today, really bridging ancient craft, Cold War tech, and cutting-edge bioengineering.
That's right.
We're talking about the evolution of personal protective equipment, specifically body armor. And we want to look past, the name everyone knows, Kevlar, to explore a future that might just be woven from things like silk and, believe it or not, carbon atoms.
Yeah, our stack of sources today is pretty rich. It covers, everything from 19th century frontier medicine all the way up to the synthetic biology labs working right now.
Okay.
Our mission really is to trace how ballistic resistance developed, try to understand the physics behind what makes armor actually work, and see how some really old ideas, like using silk, are suddenly becoming revolutionary again through modern science.
Okay, let's unpack this then. We'll start with that surprising history bit, the connection between silk and some of the very first protective vests. Then we'll dive into let's call it the brutal math of material science, comparing the big metrics for synthetic giants like Kevlar against what nature came up with, spider silk.
Right, the performance showdown.
Exactly. And finally, we'll look at the standards armor has to meet, some big design breakthroughs, some notable failures too, and then peek into this kind of nanotechnology future with materials like graphene.
Sounds like a plan. It's a great story.
So this search for armor that's light, flexible, it always seems to come back to fibers rather than just rigid plates, doesn't it?
Absolutely. Long before we had polymers, natural silk was, the obvious candidate. But the idea, so many breakthroughs, it took literally centuries for the technology to catch up and make it viable.
And this is where the story gets really surprising, right? Takes us back to Tombstone, Arizona, 1881.
Yeah, the Wild West.
Exactly. There's this frontier physician, Dr. George E. Goodfellow, and he observes this. Well, it's basically accidental field research. A guy named Charlie Storms gets shot. But he survives because a silk handkerchief, folded up tight in his breast pocket, actually stops the bullet. It absorbed enough energy so it didn't penetrate his chest.
That anecdote is just perfect, isn't it? It's kind of the accidental origin story for this whole field. Goodfellow saw what happened, realized how significant it was, and in 1887, he published an article, called it Impenetrability of Silk to Bullets.
Right to the point.
Yeah, and that observation, it almost immediately sparked commercial development over in Europe, specifically by a Polish inventor, Kazimierz Hugle.
Ah, Hugle. So he developed what we kind of recognize as the first soft vest.
Pretty much, yeah. His design used somewhere between 18 and 30 layers of heavy silk fabric.
30 layers.
Yeah, and it worked. Specifically against the bullets of the time, relatively slow, soft lead rounds from black powder handguns. The common threats back then. It was genuinely revolutionary personal protection.
Revolutionary, yes, but as you mentioned, the cost.
Oh, the cost was astronomical. Our sources say one of these vests cost $800 back in 1914.
$800.
Yeah.
In 1914 money. If you adjust that for inflation today, what is that?
It's roughly $25,000 for one vest.
$25,000.
Yeah.
So this was a standard issue for anyone. This was like luxury protection for kings or maybe gangsters with deep pockets.
Exactly. Purely for the elite. Or people who had very serious enemies. And we know they were effective. There's another incident in 1901. Another Polish inventor, Jan Szczepanik, made a silk vest that famously saved the life of King Alfonso III of Spain during an attack.
Yeah.
But the actual idea of silk armor, the concept, it goes back way further than the 19th century.
Right. This wasn't just some fluke discovery then.
Not at all. We have to talk about Gottfried Wilhelm Leibniz.
Leibniz.
The calculus guy.
The very same. Co-inventor of calculus. Between 1646 and 1716, he actually proposed using layered silk for armor. His insight was fascinating. He noted that a single silkworm cocoon is strong, but it has weak points where it attaches.
Okay.
So he suggested layering and pressing cocoons together into a kind of dense lattice structure. A lattice. Why that specific structure?
Because, he reasoned, if a projectile hit one cocoon, it might tear that cocoon. But the tear wouldn't propagate, you see. It would immediately run into the overlapping, tightly pressed structure of the cocoons next to it.
Stopping the tear from spreading.
Exactly. That fundamental idea, preventing tear propagation through layering and structural arrangement, that's pretty much the core concept behind modern fiber weaving and composite armor design today. Leibniz essentially blueprinted it centuries before the materials really existed.
That's incredible. The answer was kind of waiting in a library for 200 years.
Yeah.
So, let's move forward. Industrial era, world wars. The scale of conflict explodes, armor is needed, but flexibility and weight become huge problems.
Yeah, World War I really showed the initial failure to protect ground troops effectively.
Ah,
Early attempts were often just too localized or way too heavy. The British tried things like silk and cotton necklets, hoping to stop low-velocity shrapnel.
Necklets. Doesn't sound very comprehensive.
No. The Germans, though, they went bigger with the Sappenpanzer, nicknamed lobster armor. You can picture why. Segmented plates.
That's heavy and clunky.
It absolutely was. It was nickel and silicon steel plates, really only designed for static positions, guys in trenches, machine gunners, maybe sentries. Totally impractical for regular infantry on the move. Just too heavy, too restrictive. The lesson was clear. If you can't move, armor can actually be a death sentence.
Right. Then the interwar period is interesting because the demand shifts, right, from the battlefield to American city streets.
Gangsters.
Yeah, this is where you get that classic arms race dynamic.
Yeah.
Criminal gangs started using these relatively inexpensive vests
Uh-huh.
made of thick cotton, layers of cloth, much cheaper than silk, obviously.
It's still effective.
Effective enough against the common handgun rounds of the day, yeah. Things like the .38 Special, the .45 ACP. Suddenly, law enforcement finds their standard issue ammo just isn't cutting it anymore.
So the police have to up their game. They need more firepower. Precisely. Necessity drives innovation, or in this case, escalation. Police departments started adopting more powerful rounds, the .38 Super, and especially the really potent .357 Magnum. And that escalation instantly made those simple cotton vests pretty much obsolete, which in turn pushed armor development back towards needing more advanced materials again. It sort of set the stage for the synthetics to come.
And the synthetic revolution really kicked into high gear in World War II, but the focus shifted again, didn't it? Less about bullets, more about fragments.
Yeah, it was pragmatic. For air crews, especially bomber crews, the biggest danger wasn't necessarily a direct bullet hit, but all the low-velocity shrapnel, the fragments flying around inside the plane.
Like,
Exactly. So the British developed nylon flak jackets in 1943. Nylon was great lightweight, tough enough to catch those fragments. Meanwhile, on the ground, the U.S. military introduced vests using something called Doran plate. It was a fiberglass-based plastic. Saw its first major use at the Battle of Okinawa in 1945.
and the Soviets, they had their own approach, right?
Steel. They did. They went back to steel with the SN-42 breastplates. Spalnoy Nagrudnik, steel bib, basically. These were about 2 millimeters thick steel plates, weighed around 3.5 kilos, maybe 8 pounds.
Still pretty heavy for general use.
Yeah, generally too heavy for regular infantry. But they proved really effective in specific situations, like close quarters, urban fighting, think Stalingrad. They could actually defeat rounds from German submachine guns at close range. So a successful, if specific, return to steel armor.
Okay, but the real pivot point, the thing that changed everything for modern armor, came after the war. The age of polymers. Kevlar.
This is the big one, the permanent shift away from those older materials. 1971, Stephanie Kwolek, a research chemist at DuPont, discovers this liquid crystalline polymer solution. It becomes para-aramid fiber, trademarked as Kevlar.
And the key property.
Strength-to-weight ratio. By weight, Kevlar is about 5 times stronger than steel in tension. 5 times.
That's the game changer. Why was that specific property so critical for getting police officers to actually wear armor?
Because before Kevlar, body armor was just too heavy, too hot, too restrictive. Cops would only wear it in really high-risk situations, like a barricade or a raid. Kevlar allowed manufacturers like Richard Davis with his Second Chance Body Armor Company. He introduced the Model Y vest in 1976. It was thin, flexible enough that officers could wear it comfortably under their uniform every single day.
Making it standard procedure, not just special equipment.
Exactly. It became part of the daily uniform, and the impact was undeniable. Our sources tracked, by 2006, over 2,000 documented cases where police officers' lives were saved by their armor. These are often called saves in the industry. Kevlar proved that lightweight, flexible protection wasn't just possible, it was practical for everyday duty.
Okay, so as we shift into the nitty-gritty material science, we need to get some terminology straight first. You mentioned this earlier, but it's crucial.
Yeah.
So we never say bulletproof, right?
Absolutely critical distinction. The correct term is bullet resistant because no armor, none, can stop every possible threat. Protection is always relative, always measured against a specific standard or known threat level.
Got it. Bullet resistant. So let's compare the two main contenders we're looking at. Kevlar, the synthetic champ made from polymers, versus spider silk, nature's offering, a protein fiber, keratin-based.
Right. It's basically human synthesis versus millions of years of evolution.
And to compare them properly, we need to understand the properties that actually matter when something's trying to punch through armor at high speed. There are three key measures, aren't there?
That's right. First, tensile strength, often called UTS, ultimate tensile strength. That's the maximum pulling force a material can take before it just snaps.
Okay, raw strength.
Second, elasticity, usually measured as percent elongation. How much can it stretch before it breaks?
Flexibility, essentially.
And third, arguably the most important for ballistics, energy to break, or toughness. This is the total amount of energy the material can absorb before it ruptures. Not just strength, not just stretch, but the combination.
Okay, let's start with the one people usually think of first. Raw tensile strength. How do Kevlar and spider silk stack up there, measured in gigapascals, GPa?
Kevlar is the clear winner here, no question. Its UTS is somewhere in the range of 3.4 to 4.1 GPa.
Just to give the people a sense, 1 gigapascal is like putting a mid-sized SUV on your thumbnail.
Roughly, yeah. That kind of pressure. Kevlar can handle 3 or 4 times that before it breaks. Now, dragline spider silk, the strong stuff spiders use for the frame of their webs, typically comes in around 1.2 GPa.
So significantly less, maybe a third of Kevlar's strength.
In pure static pull, yes, Kevlar is demonstrably stronger.
Okay, so if Kevlar is 2 or 3 times stronger in raw tension, why on earth is the scientific community pouring millions into figuring out how to make spider silk artificially? What's the catch? What are we missing if we just look at UTS?
We're missing the other two factors, elasticity and that crucial energy absorption. They matter immensely when you've got a tiny projectile hitting with incredible speed and focused energy. So the second metric, elasticity. This is where silk starts to look really interesting. Untreated dragline silk can stretch a lot, between 24% and 30% of its original length before it ruptures.
24 to 30%. How does that compare to something famously flexible, like steel wire?
High carbon steel, like you find in piano wire, which is very strong and flexible, it maxes out around 25% elongation. So spider silk is right up there, or even better in terms of pure stretchiness.
Wow, okay, that stretch capacity is huge. Because if you get hit by a bullet, you don't want the material to just be rigid and shatter, right? You want it to give, to stretch, to spread that impact energy out over a wider area.
Precisely. You want it to deform gracefully. And that combination of high strength and high elasticity leads us to our third metric, energy to break, or toughness. Often measured in joules per kilogram, JKRA, this is where spider silk just dominates. The energy needed to actually break spider silk is calculated somewhere between 1.4 and 2.2 times 10 to the power of 5 J-kilograms.
Okay. And Kevlar, what's its toughness number?
Kevlar comes in around 1 times 10 to the power of 5 J-kilograms.
Wait, so carry the one. Spider silk takes roughly 3 times more energy to break than Kevlar, pound for pound.
Approximately, yes. Maybe 2 to 3 times, depending on the specific silk and Kevlar types. But significantly more. Remember, the whole point of armor isn't just to be strong. It's to absorb the bullet's energy, deform, catch it, and stop it without failing catastrophically. Silk achieves this through exceptional toughness. It absorbs that kinetic energy much more effectively.
That ratio, maybe 3 to 1 in toughness, completely flips the script. It explains why a material with lower raw tensile strength is still considered, potentially the ultimate fiber. But what's going on inside the silk at a microscopic level? How does it actually do that?
It comes down to its remarkable viscoelasticity. Think of viscoelastic materials, maybe like really high-quality memory foam or even silly putty, but incredibly strong at the same time.
Okay.
When a high-speed impact hits, the material deforms, absorbing energy. But critically, it doesn't just spring back like a rubber band. It dissipates that energy, mostly as heat. The technical way to say it is the loading and unloading paths are not collinear. It doesn't give the energy back efficiently.
So it absorbs the punch, turns it into heat and stretching, instead of just bouncing the force back.
Exactly. And our sources suggest the microstructure is key. It's thought to have 2 main components acting together. You've got stiff crystalline parts called bull-pleated sheets. Think of these like tiny, highly ordered, rigid crystals embedded in the fiber. They provide the tensile strength, the stiffness, like the rebar in concrete.
Okay, the strength component. Where does the stretch, the elasticity come from?
That comes from the other component, an amorphous, rubber-like matrix that surrounds these stiff crystals. These regions are rich in structures called I-helices. They're unordered, coiled, very flexible. They act like a shock-absorbing jacket around that stiff, crystalline skeleton.
So when the bullet hits,
When the fiber gets loaded rapidly, those flexible I-helix regions stretch out massively, absorbing and dissipating the kinetic energy. Meanwhile, the stiff foot crystals prevent the fiber from stretching too far and breaking prematurely. They provide the backbone.
that's, wow, a dual structure. Nature's engineered composite material. Stiff bits for strength, stretchy bits for toughness.
Pretty much. Kevlar, while incredibly strong, relies more heavily on its highly ordered crystalline structure for its strength. Silk achieves this amazing balance between strength and stretch, which is just ideal for absorbing that sudden localized impact energy and, crucially, reducing the blunt force trauma transferred to the person wearing it.
Okay, given that spider silk has this superior toughness, maybe 3 times that of Kevlar, the obvious question is, why aren't soldiers and police already wearing vests made of it? Why isn't it everywhere?
Yeah, it boils down to one simple, massive problem, scale. You just can't farm spiders efficiently. They're territorial. They can be cannibalistic.
Right, not exactly cooperative livestock.
Not at all. And they simply don't produce enough silk fast enough for any kind of industrial need. The cost of trying to harvest it naturally would be insane. Mass production is impossible that way.
So that's the bottleneck, material cost and just the sheer impossibility of getting enough raw material from actual spiders.
Exactly, which is why scientists and engineers turn to biotechnology, specifically recombinant production methods. The idea is to make the silk protein, it's called speedroin, without needing the spider itself.
Right, so if you can't use the spider, you take the spider's DNA, the genes for making speedroin, and you insert them into something else that is easy to farm or grow in large quantities, like biofactories.
Precisely. This is where synthetic biology comes in. And researchers have tried inserting those spider genes into all sorts of hosts. Some of the most famous early attempts involved larger animals you might have heard of, the spider goats.
Spider goats, seriously?
Seriously. They genetically modified goats so that the spider silk proteins were produced in their milk. You then milk the goat, extract the speedroin protein from the milk, purify it, and then try to solidify it into usable fibers.
That sounds complex. How successful was that?
It worked in principle. They got the protein. But scaling it up with large animals presented its own challenges, obviously. More recently, there's been huge success with silkworms.
Using an insect that already knows how to make silk.
Exactly. Chinese scientists in particular have engineered silkworms to produce hybrid silk fibers that incorporate spider DNA. And the results are pretty staggering. Some of these hybrid fibers show a 6-fold increase in toughness compared to conventional aramid fibers like Kevlar.
6 times tougher. That's revolutionary if they can scale it.
It absolutely is. The silkworm is a great host because it already has the biological machinery, the glands, to produce and spin a high-quality fiber naturally. You're just tweaking the recipe, essentially.
Okay, but there's still a challenge, right? Even if you get the protein from goat milk or engineered silkworms, you still have to turn that liquid protein solution, the speidroin, into a solid fiber that has those amazing mechanical properties. How do they do that? That sounds like the really tricky part.
It is the major engineering hurdle. It's all about biomimicry. A spider has evolved this incredibly complex set of glands that precisely control things like temperature, pH levels, salt concentrations, all to make that liquid protein solidify into a perfect fiber almost instantly as it's extruded.
And we have to replicate that artificially.
We have to try. When humans extract the speidroin from, say, milk or bacteria or yeast, it's just a liquid solution. We then have to force it through tiny holes, spinnerets, under carefully controlled chemical conditions, a process called doping and spinning to try and mimic the spider's natural process. If that artificial spinning isn't perfect...
The fiber isn't as good.
Exactly. The crucial microstructure inside the fiber, getting those boot-pleated sheets aligned just right for strength, getting the amorphous regions right for elasticity if that structure is messed up during spinning, the final fiber's performance, especially its toughness, can be severely reduced. It won't live up to the potential.
So getting the protein is one thing, but spinning it correctly is just as critical for the final ballistic performance.
Absolutely. The quality of the artificial spinning process is arguably paramount. And this is why researchers are also exploring other, potentially more efficient or sustainable biofactories. We've seen work using genetically modified yeast, which can be grown easily in large fermentation tanks, and even bacteria. Some interesting work uses photosynthetic bacteria or halophilic bacteria, salt-loving ones like Rhodovulum sulfibophyllum.
Why those specific bacteria? What's the advantage?
Sustainability and scalability, mostly. Using microorganisms means you can potentially grow them in huge vats very efficiently. And for things like photosynthetic or halophilic bacteria, the idea is you could potentially use really cheap, sustainable resources like sunlight, CO2, maybe even seawater for the salt-loving ones, instead of needing sugars or other food sources.
Cutting down the cost and environmental impact.
Exactly, compared to farming animals or even silkworms. Plus, there's ongoing research into using transgenic plants like tobacco or corn to produce spidroim. Imagine harvesting fields of corn that contains spider silk protein. That could offer really high volume, potentially low cost production down the line.
It's clear the industry is way past just theoretical ideas. This stuff is actually being tested by militaries now, isn't it? Let's talk about Craig Biocraft and their dragon silk.
Right. Craig Biocraft is one of the leading companies. They use genetically engineered silkworms incorporating DNA from a specific spider, the golden silk orb weaver, Nephila clavipes. And yes, in 2016, their technology caught the eye of the U.S. Army. The Soldier Protection and Individual Equipment Office, PEO soldier.
What did the Army do?
They awarded Craig an initial contract, about $100,000, specifically to produce and deliver samples of dragon silk for ballistic testing. They wanted to see how these shoot packs actually performed against fragments and potentially bullets.
That military interest is a huge validation, isn't it? It shows spider silk isn't just some sci-fi dream anymore.
Not at all. It's being taken very seriously. The COO of Craig Biocraft noted at the time that while their dragon silk maybe had slightly lower tensile strength than commercial Kevlar, maybe around 2 GPa compared to Kevlar's 3-4 GPa, its incredible toughness, that energy absorption, made it potentially ideal for applications where lightweight flexibility is key. Think fragment protection liners or maybe super flexible vests for certain roles.
So maybe not replacing Kevlar entirely, but complementing it, using it in hybrid systems.
That seems to be the strategy, yeah. Combine the best properties of both. Use dragon silk for its toughness and flexibility, maybe layer it with Kevlar for raw strength, create hybrid materials that outperform either one alone.
And Craig isn't the only player. You mentioned other companies getting funding even earlier.
That's right. Companies like Remat, now called Refactored Materials, received U.S. government funding way back in 2010. They got a Small Business Innovation Research, or SBIR, grant specifically to develop high-performance ballistic fibers derived from spider silk. So this race to industrialize biological armor, it's been running seriously for well over a decade now.
Okay, so we have all this amazing material science, Kevlar, steel plates, maybe spider silk soon, maybe graphene down the road. But none of it matters if it doesn't actually meet the required performance standards, right? And these standards aren't universal.
Absolutely not. They're very regional. They have to reflect the specific threats that soldiers or police officers are most likely to face in their area of operation.
So in the U.S., we mostly hear about the NIJ standards, National Institute of Justice. What are some of the other big ones internationally?
Well, you've got the UK's standard, which comes from their Home Office Scientific Development Branch, or HOSDB. Germany has the VPM standards, and then there's the Russian GOEST standard, which is generally considered extremely stringent.
Why the difference? Why are some so much tougher than others?
It often comes down to common ammunition types. For example, the 7.62 by 25 millimeter Tokarev pistol round is really common in Russia and former Soviet countries. It's a relatively small, high-velocity round, and it's notorious for being able to penetrate standard NIJ Level 3A soft armor, which is common police issue in the West.
So Russian standards have to be higher just to deal with that prevalent threat.
Exactly. Their baseline needs to account for the Tokarev threat. Now, if you compare the highest rifle protection level, say US NIJ Level 4, against the Russian GOEST 6A, there's a really significant difference in how they measure the effect of the bullet hitting the plate, even if it doesn't go through.
Okay, tell us about that. What's the key difference?
It's about stringency, especially regarding multiple hits and something called back face deformation, or BFD.
Back face deformation. Okay, that sounds important. What is it?
BFD is the measure of how much the armor plate bulges or deforms inward towards the wearer's body when it gets hit by a bullet, even if the bullet is stopped. All that kinetic energy has to go somewhere, right?
Right. It pushes the plate back.
Exactly. A high BFD is like taking a really severe punch in that exact spot. Now, the highest Russian standard, GOC 6A, it requires the armor to stop 3 hits of a specific armor-piercing incendiary rifle round, the 7.62 by 54 millimeter B32. But critically, it allows a maximum BFD of only 16 millimeters.
16 millimeters. That's just over half an inch. How does that compare to the U.S. NIJ Level FU standard?
NIJ Level 4 is designed to stop 1 hit of a powerful armor-piercing rifle round, the .3006 M2AP, but it allows a BFD up to 44 millimeters.
44 millimeters. That's almost 2 inches. That sounds dangerous, even if the bullet doesn't penetrate.
It can be very dangerous. That much deformation, almost 2 inches pushing into your torso, can cause severe blunt force trauma. We're talking broken ribs, internal bleeding, damage to organs like the heart or lungs, especially if the impact is centered on the chest. It can be lethal even without penetration.
So the much lower 16 millimeter limit in the GHOST standard is specifically designed to prevent those potentially fatal internal injuries.
That's the idea. It makes the GO 6A arguably a much stricter standard when it comes to mitigating that behind-armor blunt trauma.
Which leads us perfectly to the solution designed specifically to deal with BFD, trauma plates or trauma pads.
Exactly. These are crucial components. They're usually non-ballistic themselves, meaning they don't stop bullets on their own. They sit behind the main hard armor plate. Their job is purely to absorb and spread out that residual impact energy, the energy that causes the BFD.
So they cushion the blow.
Right. They're often made of materials with good viscoelastic properties, specifically designed to manage that final impact, significantly reducing the depth of that back face deformation and lowering the risk of serious internal injury. Very important piece of the system.
Okay, so armor isn't just about stopping high-speed bullets. Protection often needs to cover other threats, especially for police or corrections officers. Stabbing, slashing.
Absolutely. This led to a whole different branch of vest development, particularly focused on stabbing threats. In the mid-1980s, the California Department of Corrections realized they had a major problem with inmates using sharpened objects, basically homemade shanks or ice picks.
Things that don't cut but puncture with high force.
Exactly. A smooth, pointed object like an ice pick doesn't necessarily cut fibers like Kevlar. It tries to push them aside or penetrate between the weave. So California issued a requirement for vests that could stop a specific ice pick threat, a high-impact puncture test, delivering 109 joules of energy.
And could standard Kevlar vests handle that?
Not initially. Early solutions needed stiff plates. But eventually, specialized textiles were developed, things like turtle skin, which uses extremely tightly woven para-aramid fibers. The weave is so tight, the smooth point of the ice pick can't easily find a gap to push through, and it can't cut the strong fibers. It forces the impact energy to spread out laterally across the weave, stopping the penetration.
Okay, so that's for a non-cutting puncture.
Yeah.
How did the UK approach stab protection? Their HOSDB standards seem different.
They are. The UK standards were developed partly in response to threats like broken bottles or purpose-made fighting knives, things that do cut. They created specific engineered test blades, the S1 blade for general stabbing, the P1 blade, which mimics a hypodermic needle or ice pick, and they tested against simulated human attack energies, up to 45 joules and specific velocities.
And because these threats involved actual cutting edges.
Because they involved cutting, standard woven aramids often weren't enough on their own. The blades could sever the fibers. So UK standard stab vests often have to incorporate other materials. Sometimes metallic components like thin sheets of flexible steel or aluminum, or even layers of fine chainmail are combined with the textiles. This results in what are called multi-threat vests, which can be quite dense and heavy, like those often worn by police in London.
Right. Okay, moving from soft armor and stab vests back to hard armor, the plates needed for rifle rounds.
Yeah.
Ceramics are the standard, right? SAPI plates, ESAPI plates in the military. But they have issues.
They do. The main ones are weight. They're heavy and limited multi-hit capability. Standard armor plates are often monolithic, meaning they're basically one large ceramic tile bonded to a fiber backing.
And when that gets hit?
When a high-velocity rifle round hits that monolithic plate, the ceramic shatters. It absorbs the energy by breaking, which is good, but the impact creates large cracks that radiate out from the hit point. This compromises the structural integrity of the plate around the impact zone.
meaning it can't reliably stop another bullet hitting nearby.
Exactly. Subsequent shots hitting close to the first impact are much more likely to penetrate because the ceramic in that area is already damaged. This limitation drove a lot of research into non-monolithic designs.
And we have a couple of key examples here. One famous failure and one perhaps less famous success.
Right. The failure was the dragon skin body armor system. The concept was appealing. Instead of one big plate, it used an array of small, overlapping ceramic discs, kind of like scales. The idea was it would be more flexible and offer better multi-hit protection because only the discs directly hit would break.
Sounds good on paper. What went wrong?
It proved fundamentally unreliable in testing, especially under realistic environmental conditions. Military tests showed that the adhesive holding the discs together could fail after exposure to high temperatures, like over 120 degrees Fahrenheit, or even just after being dropped. This compromised the whole system.
And the ballistic performance suffered.
Dramatically. In tests against the standard M2AP armor-piercing threat, dragon skin reportedly suffered 13 complete penetrations out of 48 shots. That's a catastrophic failure rate. The whole program was basically scrapped because it just wasn't reliable enough for soldiers.
Okay, so dragon skin failed. What's the example of a successful non-monolithic approach?
A system called LABA, Light Improved Body Armor. This also uses an array of small ceramic elements, but instead of overlapping flexible scales, it typically uses ceramic pellets or small tiles embedded rigidly onto a backing material. It's not flexible like dragon skin was supposed to be, but it offers excellent multi-hit performance.
How good.
Field reports and testing showed LEBA plates could potentially withstand numerous hits, maybe up to 15 rounds from something like an AKM rifle, impacting different areas of the plate, and still prevent penetration, maybe causing only minor bruising. It proved that breaking the plate up into smaller, isolated ceramic units was a viable way to manage multi-hit threats much better than a single large plate.
Okay, fascinating. So finally, let's look even further ahead. Beyond ceramics, beyond even bioengineered silk, the ultimate material science frontier seems to be graphene.
Graphene is definitely where a lot of future gazing is focused. It's that incredible material, a single layer of carbon atoms arranged in a perfect honeycomb lattice. It's the thinnest material imaginable, incredibly light and astonishingly strong. We're talking maybe 200 times the tensile strength of steel.
200 times steel.
Wow.
But for ballistics, is it just about strength? Or does it have that energy dissipation quality too?
That's the really exciting part. Research, particularly from Rice University, found that when it comes to dissipating energy from a microscopic impact, graphene is about 10 times better than steel.
10 times better at absorbing the shock. But how fast does it do that? That seems key for stopping a bullet.
This is the mind-blowing number. Researchers at the University of Massachusetts did experiments firing tiny silica bullets at stacks of graphene sheets just a few layers thick. They measured how quickly the impact energy spread through the graphene layers. In the incredibly brief time the sheets held together, we're talking about 3 nanoseconds, the kinetic energy transferred through the graphene at a speed of 22.2 kilometers per second.
22 kilometers per second. That's insane. What is that, like almost 70 times the speed of sound?
Yeah.
Rifle bullet travels at maybe 1 kilometer per second.
Exactly. That speed of energy dissipation is just phenomenal. It suggests the material is essentially spreading the impact energy out sideways so fast that it neutralizes the force almost instantaneously before it can punch through the layers vertically.
So if engineers can figure out how to make large defect-free sheets of graphene affordably and how to layer it or integrate it into composites for armor,
it holds the potential for revolutionary protection. Armor that could be incredibly thin, incredibly light, maybe even flexible, yet capable of stopping threats that are simply too much for current materials. It leverages the perfect structure of carbon at the atomic level to achieve that ultimate lightweight, high-performance armor.
Wow. So we've really covered a huge span here. From, that accidental discovery with the silk handkerchief and tombstone back in 1881, through Leibniz's ideas that were centuries ahead of their time, the rise of synthetics like Kevlar, the amazing potential of bioengineered spider silk from goats or silkworms, and now looking towards graphene moving energy at nearly 70 times the speed of sound. The whole story of personal protection is really one of material science, constantly racing to stay ahead of the threats.
It absolutely is. And I think for you, the listener, one of the most fascinating takeaways is that strategic shift we're seeing, moving away from purely creating artificial materials like the polymers in Kevlar towards harnessing and scaling up nature's best solutions, like spider silk, using advanced biotechnology.
Yeah.
And that reliance on genetic engineering, on recombinant DNA, putting spider genes into silkworms or bacteria, it really forces us to think about the implications, right?
Yeah.
How do we manage the ethics, the sustainability, the intellectual property when our defense technologies start becoming intertwined with biology itself?
That's a really profound thought. And it makes you consider that fundamental trade-off we've discussed, balancing raw strength like Kevlar's high GPA against that critical energy dissipation and elasticity you get from silk or maybe graphene. How will mastering that balance define not just the body armor of tomorrow, but maybe also the cars we drive, the buildings we live in, making everything lighter, stronger, and fundamentally safer by design?